Hello again. We are continuing our discussion on exponents and exponential functions by talking about geometric sequences. It seems to be an unrelated topic, but it actually will be quite related to exponential functions. So I want you to think back to when we were talking about arithmetic sequences. We start with a number and we keep adding the common difference to get the next term. So things like 3, 5, 7, 9, 11, that starts at 3 and goes up by 2's. 10, 8, 6, 4, 2, that starts at 10 and goes down by 2's every time. 4, 15, 26, 37, 48, that starts at 4 and goes up by 9's, or actually by 11's every time. Sorry about that. Goes up by 11 every time. So that's what arithmetic sequences do. Geometric sequences are different in that you start with a number, but instead of adding the same thing over and over again, you multiply by the same thing over and over again. That's the only difference. So things like 2, 6, 18, 54, I'm starting at 2 and I keep multiplying by 3 over and over again. 128, 64, 32, 16, I start at 128 and I multiply by a half, or I divide by 2 to get from every term to the next term. 1, 5, 25, 125, same thing, I'm starting at 1 and I keep multiplying by 5 to get to the next term and the next term and the next term. So all of those are geometric sequences, not arithmetic. So does that pattern remind you of anything? Well, let's consider a geometric sequence that starts at 5 and has a common ratio of 5. The first term would be 5, second term would be 25 because I would multiply that 5 by 5. Multiply by 5 again and the third term is 125. Multiply by 5 again, and I get 625. Now let's consider an exponential function that is f of x equals 5 to the x, using the same number that I used for the geometric sequence. Well, f of 1 is 5. F of 2 is going to be 5 to the 2, which is 25. F of 3 is going to be 5 to the 3, which is 125. F of 4 is going to be 5 to the 4, which is 625. And look, I'm getting the same numbers in both columns. One was a geometric sequence, one was an exponential function. So they are indeed related to each other. Okay? We're getting the same thing. So we need to be able to convert every geometric sequence to an exponential function. Okay, here's how I do that. A is going to be the first term of the sequence. R is going to be what I keep multiplying by over and over again to get the next term. That's called the common ratio. Remember, it was called the common difference for arithmetic sequences. Now it's a ratio. Okay, so the function is written like that. Y equals A times R to the x minus 1. A and R will have to be replaced with numbers that I give you, but the Y and the X can stay as Y and X. Okay, so in this case, the first term is 6, so A is going to equal 6, and it's going to be multiplied by 3, so R is 3. I'm just going through an example. That means that the function is going to be 6 times 3 to the x minus 1, and that's the sequence I get. X goes 1, 2, 3, 4. Y starts at 6 and goes up, or gets multiplied by 3's from term to term. Okay, here's another one. I have a first term of 5, so A is going to equal 5. Then I'm going to multiply every term by 0.4, so that means that R is 0.4. So the function is going to be 5 times 0.4 to the x minus 1. So the x's go 1, 2, 3, 4. The y's start at 5 and get multiplied by 0.4 with each one. All right, so that is geometric sequences and what they have to do with exponential functions. If you have any questions, please let me know, and I will see you tomorrow.